Well, how's it going, everyone? I'll go double time here to try and get us back on track. But I'm going to talk to you today about the topic of my honours, which I did at JCU with Carl Spandler, who's now at Uni of Adelaide. And that was on rare earths and other critical metals in highly fractionated volcanics. So instead of doing a kind of a broad overview of the projects going on, I decided to do more of like a focused look at this one specific type of mineralization, as it's one that not many people have really heard about, and consequently there hasn't been much either academic or industry work done on them. So I'll start with a photo of the peak ranges here. Just look here. So this is looking northwest along the peak ranges. We're in central Queensland here, and that road that runs through the centre of the image there, if you go to the left in about 30 kilometres, you get to Capella, and Dysart is about 30 kilometres on your right. So it's in the middle of the Northern Bowen Basin there. All right, so highly fractionated volcanics. As the name would suggest, the melts that form these things result from the extreme crystal fractionation of parental lavas. So we're talking on the order of about 90% crystallization, and that remaining 10% or even less of melt being the parental melt behind these HFVs. So the primary fractionating processes that happen within these magma chambers, they can have the effect of concentrating certain elements in the melt. And these are usually referred to as incompatible elements that aren't compatible in any of the crystallizing mineral phases, and as a result end up in the remaining melt. So if conditions are right, and it requires special chemistry as well as physical conditions to get this, these enrichments can include the rare metals or critical metals, rare earths, zirconium, hafnium, niobium, tantalum, which are as well all new economy minerals, as they've recently been called by the government. So if these last little bits of melt erupt to the surface, then the result are large outcropping and generally quite homogeneous rare metal enriched volcanic units. And these have been described, and I think it's a pretty good way of describing them, as the rare metal analog to the copper porphyry. So we're talking low grades and not your flashy 10% plus grades you get with carbonatites, but we're talking hundreds of millions of tons, if not billions of tons. So I've just included a little graphic here, which was Carl and Meyer's interpretation of the formation of the peak range volcanics, because it kind of shows all the ingredients that you need to have highly fractionated volcanic rare metal mineralization. You need to start with fertile primitive magma that has the ingredients already. So one of the best ways to do this, and one of the ways that Queensland sees this, is with mantle plume related melts. You need extended fractionation, and this can happen at various positions in the crust. And potentially even multiple positions in the crust with a lower and then an upper period of fractionation. And then you need a rapid eruption to the surface. If you don't rapidly erupt these melts to the surface and instead place them in the crust, you might get something like a rare metal granite instead, which we see in other places across the globe. But in Queensland, we generally see them as volcanics. So there are currently a few investigated examples of this style of mineralization. There's not many, granted, and there's no currently producing mines on these, but there are a few kind of advanced stages of investigation. And one of which that I'll talk about in a little bit more detail is Roundtop. So Roundtop is a rhyolite laccolith in Texas over in the States. It's owned by a company called Texas Mineral Resources, who are, by the way, up 100% this month on the back of some good metallurgy results. It's low grade, as you can see, so it's only 0.06% total rare earth oxide, so 600 ppm total rare earths, but it's very large tonnage. The ore is processed via ion exchange, ion chromatography, and the whole idea behind building this mine here is to take it from mineral to metal on site. So we're actually calling it mine to magnet, as their main output will be rare earth magnets. And there's obviously a lot of added value there. If you can, instead of shipping off concentrate, you can ship off magnets straight from site. So the pilot plant should be up and running just about any day now. And as you might imagine, this has attracted quite a bit of attention as the US are kind of focusing more and more on establishing a domestic supply chain for these things. So Trump's a big fan of things like this. So Queensland has quite a few highly fractionated volcanics, and most of these, or at least the ones that I'm interested in, are typically associated with young, so less than 35 million year old interplate volcanism, of which Eastern Australia has a huge amount of. So there are two main types of volcanism in Queensland. One of these are lava-filled provinces, which I have up on this diagram here. in green. So these generally just involve basalts. So yes, they are mantle melts most likely, but they didn't have the fractionating stage to get to your trachytes and your rhyolites and your more evolved members. So they're generally not too prospective for this style of mineralization. However, the other one, which are called central volcano provinces, they have early basalts, but they also have later intermediate to felsic volcanics that outcrop through and erupt on top of the early basalts. So as these intermediate to felsic volcanics, they're often related to these early basalts via processes such as crystal fractionation or crustal assimilation. They have the potential to have this style of mineralization. So if we look at the peaks, the ones that we have in Queensland, there are about 7 central volcano provinces. Oh, sharing the screen there. And they kind of appear in 2 groups. So we have one group that's up in the north that involves the Hillsborough to Buckland trend and involves 5 separate ones, of which the Peak Range is one of them. And then we have a southern group, which involves Main Range and Tweed. So we have quite a lot up in Queensland. So zooming in to the Peak Ranges, the Peak Ranges outcrop in the Central Bowen Basin, and they potentially outcrop along a Tasmanite boundary. So if we have a look at the little inset map here on figure A, we can see that it kind of sits right on the boundary between the New England origin on the east and the Thompson origin on the west. And this lithospheric structure may have provided somewhat of a conduit for these mantle melts to get to the surface. So the regional flood basalts, which are on this map here in tan colour, have been dated between about 47 and 26 million years old. And then there are 2 intermediate to felsic groups of volcanics associated with these basalts. So you have a northern periluminous group, which is up here, and this is clustered around an older intrusive complex. And this is about 30 million years old, these ones here. And then you have a southern peralkaline group, which are slightly younger than the northern group at 29 million years old. So the southern Peak Range volcanics were the subject of my honours thesis. So we spent a lot of time having a look around these mountains. And as you can see, it's actually a pretty spectacular landscape with some pretty dramatic peaks down there. So there are about 20 or so discrete volcanic bodies within that area down there. And we found that there were 5 dominant rock types, which can be split up based on their mafic mineralogy and their silica content. So we have 2 types of trachyte. We have augite-bearing trachytes and hornblende-bearing trachytes. And we have 3 distinct types of rhyolite. So we have hornblende-bearing rhyolite, our fredsonite rhyolite. So this has our fredsonite, which is a sodium amphibole species in it. And we have adrian rhyolite, and adrian is a sodium pyroxide. So these 3 mafic minerals also impart a colour into the rock. So the hornblende rhyolites are a distinctive tanny brown colour, whereas the fredsonite rhyolites are a bright blue colour and the adrian rhyolites are a bright green. So it's really easy to identify these rock types in the field. So each rock type can be related to each other as representing a periodically erupting closed magmatic system that is dominated by crystal fractionation as the main mechanism of melt evolution. And this goes from our least evolved augite trachytes through to our most evolved adrian rhyolites, as I'll talk about in a little bit. One of these I'll draw your attention to, which I'll talk a bit more about later, is number 3 here, which I've called Claras Dome after the landholder. And as you can see by the sampling density, I sampled that quite a lot because it's quite interesting. And if we look on this profile down here, it's this little symmetrical dome here. So not quite as imposing as some of the other bodies. So me and Carl and some other hands went down there and took a lot of rock chips out of it, got these analysed, and these are plotted on these graphs here. So they're relatively standard trachytes through to rhyolites, which with a bit of a clustering in the rhyolite field. So a lot of rocks with similar major element composition. They tend to be quite peralkaline, in particular the adrian rhyolites, which are displayed in green on these figures in here. As you can see, they have a peralkaline index up to 1.3, and that's just the molar sodium plus potassium over aluminium. Riebeckite rhyolites, fredsonite rhyolites, I apologise, are also somewhat peralkaline as well. But the really interesting thing about these is they're extremely enriched in rare metals. So we're talking zirconium up to 5,500 ppm, niobium up to 900 ppm, and total rare earth element up to about 3,000 ppm. So incredibly enriched in these new economy minerals, and which might make them slightly more than just academically interesting. If we have a look at the zirconium versus silica diagram, which is down the bottom left there, we can see that the adrian rhyolites are really the ones that are super enriched in this zirconium. And while the other ones are too, I mean, you can't really sniff at 3,000 ppm zirconium. They pale in comparison to the Adrian rhyolites. If we look at figure D here, where I've got niobium against zirconium, there's a relatively good linear relationship between these two elements here, as well as the total rare earth elements as well. So where you have high zirconium, you have high niobium, you have high total rare earths. It's kind of a fortuitous grouping. So Claras Dome is one of the Adrian rhyolite bodies in the field area, and I'll just talk about this one a little bit now. So it's about 1.3 kilometers in diameter, and it's about 200 meters high, so it's a very significant mountain there. And it's a relatively structureless, a relatively featureless, pale green outcropping rhyolite, and this is kind of a typical outcrop in the bottom left here, so you can't really miss it. Macroscopically, it is relatively simple mineralogy. So it has these clusters of alkali feldspar and quartz that are in a fine-grained ground mass of quartz Adrian, so the sodium pyroxene and more alkali feldspar. This is variably overprinted with alteration, and you kind of get your typical alteration minerals like chlorites and aluminosilicate clays, as well as a bit of weathering of the alkali feldspars, and with iron oxide staining, that sort of stuff. So it's relatively simple looking at standing back and looking at it. However, we know from the chemistry that there's obviously some other stuff going on. But if you want to see, you have to get a bit closer. So these next images are all taken on the SEM. And if you look at the scale bars there, so 15 microns or 30 microns, they're really, really fine-grained, this sort of mineralogy. So there are two primary rare metal buried minerals that we found in there. And these are eudylite group minerals, which is a rare earth zirconium alkali barium silicate, and daliite, which is a potassium zircono-barium silicate. So these are kind of unusual minerals and more what you'd expect in the kind of layered nepheline cyanites over in Greenland and Russia, as opposed to volcanics here in Queensland. And from the textures, as you can see in the top two images here, they occur alongside Adrian in this late-stage magmatic association to the rest of the ground mass minerals. So the way to interpret this is that these are really the very last thing to form before the entire rock crystallized. Probably it was erupting and these things were still liquid until it finally settled and they finally cooled in these interstitial pockets to the other ground mass minerals. These rare earth and rare metal bearing minerals seem to be pretty susceptible to weathering, because where you have that alteration that I was talking about earlier, you don't have any of these primary minerals and instead have things like rare earth carbonates. So if you look at the bottom left image here on C, you have this intricate bladed textured rare earth carbonates that are probably similar to bastnasite or something like that. And you have things like amorphous zircon. So this is actually a hydrous zircon mineraloid sort of type thing that's quite unusual. And it usually occurs in this kind of vug filling, feathery sort of texture. So with the interest in mineralogy and the chemistry combined, you kind of can start thinking that there might be a bit of economic potential to these sort of things. So I've estimated the volume of Claras Dome just down to the ground. So this is because we don't know anything about the geometry under the ground. There's about 250 million tonnes of above ground Adrian rhyolite there. And the average oxide grades that we got from 21 surface samples across the dome is 0.6% zirconium oxide, 0.15% total rare earth oxide, and 0.1% niobium oxide. And the best oxide grades we got are a little bit better, but it's remarkably homogeneous across the entire thing. So if you kind of compare that to what they're working with over at Roundtop in the States, which is a similar tonnage, significantly lower total rare earths, albeit with a bit of lithium, you might be able to think that these could potentially represent sort of Australia's Roundtop, if you will. So Claras Dome is just one of three almost identical Adrian rhyolite bodies. So we're talking on the order of well over 500 million tonnes of this material in this central Queensland region. So this is an area currently being explored by NorthX with Stu Parker, who asked a question before. And yeah, we're finding some really interesting stuff and hopefully going to put a drill hole into one of these soon. So another interesting thing that came out of this study was this is really the first time that any of these central volcano provinces have been looked at for their economic potential in this sort of commodity. People have sniffed around them for gold and other things and haven't found much. However, no one's really had a concerted look for this style of new economy polymetallic mineralization in these areas. So Peak Range is just one of 7 central volcano provinces we have in Queensland. And I think it's probably the only one from the attention me and Carl and NorthX have given it now that has had any economic attention paid to it whatsoever. the conditions met there, so the fertile mantle melts, the fractionation and the eruption, are hardly unique to Peaks ranges. And I think there's a whole lot of potential in some of these other central volcano provinces. And that's the topic of ongoing research of myself, Carl, GSQ, and some other collaborators. Well, I'll finish off there. So hopefully that got us a little bit more back on track.
Thank you so much, Ross. And finishing with a pretty good picture there. So that's awesome. Thank you. We did have a couple of questions for you. Now I'm going to stuff this one right up. What range in agpatic index do you have in the peak volcanics?
Well, if by agpatic index you're just referring to the old phrase for peralkaline index, then we have up to 1.3 in the Adrian rhyolite domes. All of the rhyolites in there are either peralkaline or just slightly metaluminous, whereas most of the trachytes are entirely metaluminous. And they are agpatic, as in they have exotic rare earth buried minerals in them. Yeah.
Awesome. And Paul Gauss is very interesting, Ross. How does the rare earth mineralogy at Roundtop compare to Claras Dome? Is it also eudialyte group minerals?
So Roundtop, to the best of my knowledge, Roundtop has a combination of phosphates and carbonates. So that, as we heard earlier from Kate, these are ones that have been more readily processed, and that might be a game changer in the economic exploitation of these things. So I think it's predominantly in phosphates over there, but I'm not sure. I don't think it's eudialyte group minerals. Roundtop's actually not peralkaline. So this talk was initially titled the peralkaline volcanics, but I think it's more accurate to entitle these as highly fractionated volcanics, as you don't necessarily need peralkalinity to get these things.
Awesome. Joe Potter says, what's the rare earth breakdown for the Peaks range analyses?
Off the top of my head, we're looking at about 500 ppm niobium, 500 ppm neodymium, I should say, for some of our best analyses, with high lanthanum and cerium as well. The other benefit that we have to them too is they have relatively high heavy rare earths, especially when compared to carbonatites, which are notoriously heavy rare earth poor.
My daughter's just arrived home. So instant distraction. And Gary is asking, what properties of these lower grade rare earth deposits are potentially economic as compared to higher grade carbonatite hosted rare earth deposits?
Well, there's a few. So for starters, this is a really new style of mineralization. And as I mentioned before, there are currently no operating mines on this type of deposit. So at the moment, it's somewhat of an unproven entity. However, with positive results coming out of places like Roundtop and out of places like Tungi, which I haven't mentioned in this talk, but people might have heard of, there is potential in there. I think the biggest potential for them is, one, you can utilize bulk mining methods much easier than you can on these smaller ones. It'd essentially be more of a quarry operation than it would be an actual mine, so it should be very, very cheap to operate. And the second is the polymetallic nature. With rare earths, you're also getting zirconium, you're also getting hafnium, which I think at the moment is $600 a kilo, and you're getting niobium and you're getting tantalum as well. So these are kind of a polymetallic new economy mineral deposit, which a carbonatite, which might be solely rare earths, doesn't have that advantage.
And Joe is saying, is the balance of the different rare earths similar to Roundtop?
To the best of my knowledge, it is. And as you saw from the numbers, it actually looks significantly better than Roundtop. Yeah.